Okay.
Oh, let's try. If it works, okay. Otherwise, then it will be the quality. It's far away. It's not the same.
Okay.
Do you want to put the computer on?
Ready? Yeah. There's a problem. Okay. I'm going to show you how to install the software. At the end of the meeting, I'm going to give you one CD, one for each partner. It contains the setup software, installation notes, full manual, and a tutorial manual, which is a reduced version that contains not so many details. In most cases, not needed for a normal operation of the software. Okay? So I'm going to show you.
It's just for operational work.
Sorry?
To use the system or whatever.
Yeah, you can use it. No problem. It's the same copy, but it's not here. It's one of the CDs. I'm going to show you how to. I'm going to show you how to install it. In the CD, you'll see these files. This is the installation notes, the manual, and the tutorial. I'm going to try to follow a little bit the tutorial. And this is the setup. So you just run the setup. In your computers. Perhaps it will go a bit slower because of I have never tried to run it with this GoToMeeting. Yes, right, this is a screenshot at the beginning. Here, it's also contained the installation notes, but it will also mention here the requirements you need to have installed in your computer before installing the software. This is the Visual Studio 2012 runtime and the Net framework. This is usually installed in Windows 8 by default, so you probably will not need to install it.
The source code?
Source code? No. This is only runtime.
Okay. Okay, .NET is not.
Yeah, this is .NET framework 4.5.
Yeah. The runtime. What do you mean?
This is the Visual Studio runtime because of the CUDA code. Okay. Because it's made with a DLL written in C++.
Okay.
So, in most cases, it's probably you have already installed because this software is usually installed by other software. For instance, when you install Office or any other software, some software installs the software by default. Anyway, I give you the links. You can go to the link and download it. So it's no problem. It's free software. In your case, if you have the development tools, you probably have them already installed, and you don't need to do anything at all. Yes, set up and go.
Yeah, normally you don't need it.
Yeah. Okay. Next, a license. At this moment, I just put a generic message. This software belongs to the Scolio-SEE beneficiaries, blah, blah, blah. Installation folder. By default, I'm going to start here. Okay? You can choose another folder if you wish. Click install. This will copy the files to the hard disk. Okay? Okay, finish. So here you see an icon, start application. And if we go to the hard disk, you will see here is the folder created by the setup. The uninstalled software. Here is the binaries, executables, DLL, kind of dependencies. So, at the end, once it's installed, click on the icon, or you can also search for the icon here, and you'll see these two windows. Okay, this blue one, I have called the main window. This is where all the data will be displayed. I mean, X-ray information, competitive information, spine curves interpolation. All the visualization will be done here. This other window, I call it the controls window, contains all the buttons, sliders, options you have to set to tell the program what you want. Okay? So you mainly will be working here. This is also described in the tutorial, so you can follow. It's quite simple. It's just a step by step. You can move each window independently, one of another. If you close it because you wish or accidentally, you can reopen it again. Okay. Here, this menu only contains an option to hide and show this window, and just the exit to exit the application definitively. Okay. So we can start doing the most basic operation, perhaps loading a formatted file. For instance, a typical is at 0, something like that. So I have previously copied to this computer your original database of 10 patients. I have not distributed these files with the software because we don't know what are the ethical issues, blah, blah, blah later, so I prefer distributing the software without any data from any patient. You should give the information of the patient. Yeah, just to avoid issues. Later, if we need to delete all the patient's information, it's okay. You could keep the software and you can keep using your whole patient's data. But that's why I prefer.
It's only a tool.
Yeah. I will give only the tool. The data is up to you. I'm using this because at this moment we are in the project and we can use it. In the future, I don't know. So let's load an init. When you click this button over here, you open a window and let you choose a box, a formatting values. The first one, for instance, this one. Okay, it gives you some information. It's not really important. And here is the file. Okay, you can. These dots are the dots included in the formatted file. There is also some additional information I'm going to display later. You'll see behind there is this kind of dots. It's a representation of the dots of the formatted file we use to make the matching, the registration between both formatted files. Let's load the second one. So I click like on load init 1 or T1. We can search for the file you wish. This one, for instance, the information, and now both are loaded. You can, if you click on either side of the window, you'll see the background change the color. That means you are manipulating this or this one. So if I click there, now I can rotate the formatting with the left button. I can zoom with the wheel, the mouse. I can also translate or pan. This is only for visualization. It's not what perhaps you need to see, I don't know, whatever thing. Okay? So it's the weapon. But I'm going to show you. Now in most cases, well, the following thing you are going to do in most cases is well, I can explain you some things before. Is I'm going to explain you some more options. In this case, you can enable or disable the visualization of the formatting. This is not useful at this moment, but later you will see there are lots of overlap information, and in some cases you need to hide temporarily the formatting or else thing. You can also change the size of the dots, of the geometry, for a better visualization. This is mainly aesthetic. It's not. It hasn't any real. It's just for a better visualization in some cases. It's not very important. In some cases, it's interesting to have the impression of having a continuous surface. Okay? Also, you can change the kind of information you are displaying on the window. In this case, this color is obtained from the normal information to the back of the surface. But you can also visualize with this button. You get some options for visualization. You can show the Gauss curvature for its geometric, or the mean curvature, or just this is just flat color. I usually have the normal information enabled. Okay, you can also change the size of the dots here if you wish. Okay. Once you have these, you'll see there are this kind of green points behind the surface. This is known as the coverage. The coverage represents a percentage of the points you get from this geometric to match this one. So the more points you get here, the more accurate will be the matching between both geometrics. But it will be also very expensive from a computational point of view. So by default, I use a 10% value. If you have poor results, if you like to improve the matching, you can increase this value. I can show you. This is critical to get good results. So here I'm reducing. Now there are a few points. You can go to very high values. It's not normal to go to these values.
So you use as the original points, the point cloud from 5?
Yeah, these points are selected from the data contained in the geometric.
Okay.
Are not
3 millimeter grid.
Yeah, for the millimetric grid. From a row and a column in the geometric. It's not new geometry. It's selected from the information in the geometric. Okay? So 10% is okay, but in some cases, for instance, I go to 25 or 30. It's a bit, in some cases you need some experimentation. You'll see, I'll explain later what you need to change that value. So, for instance, in this situation, we can create a matching. You see this button here, behind the option, matching. Yes. Click. Now this is running in the GPU. It will take some seconds. This is done with the same hardware as well. Try it. It's okay. And we get this mesh. I will explain later what it is. If I increase this, for instance, to, I don't know, 30%, you see there are more points now. The computation will take some more time.
It's faster than before. It was like 5 minutes.
In some cases, it could be faster because of the organization of the information in the GPU. In some cases, the information is more easily divided into the GPU. So sometimes, okay, this is strange. I increase the coverage, but the computation time is not higher. It is lower. The mistake, you can see, it's 24 seconds. Okay? So what this kind of mesh represents? This mesh represents, what you see vertex here, or clusters of vertex, means similar zones in both geometric files. You see, for instance, the shape here is also present here. This shape here is also present here. So zones with higher similarities have bigger concentrations of points in both meshes. So again, this mesh is later used for the interpolation. So to make a matching, to make a symmetry, the symmetry, I'm going to do that. This one is similar to a matching, but it's a special matching. It's a matching between this geometric field, geometric file, and itself, but flip, like a mirror. Okay, I'm going to show you today. It's a similar process. It's in fact even a little bit more expensive. Computation time.
So you flip around what axis? Which axis do you flip around?
You make a matching between this 0 and itself, but flip. It's the same operation. It's the same operation, but with different data. Okay? So this symmetry calculates similarities on both sides of the back. What you do then? In most cases, you will also have, for this, in most cases you'll have an X-ray image, initially taken in a clinic, blah, 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 or in any other place. So we can load the X-ray for this, for instance, is this one. Okay, you notice at this moment is not aligned. The X-ray is moved slightly to the right. Why? Because at this moment we have no information about the mapping that Vasilis is doing. So we can not guess what's the right position and size at this moment. But once you got the spine curve generated by Vasilis in Word Package 4, we have already done it for you. You can load it. I have here the curve. I load it. So now you see now the size and the alignment between both is correct. There could be some errors, but most errors are due to the top and bottom point selection or distortions in the X-ray. For instance, some X-rays have inclusion deformation, different kinds of deformations. And this is the spinal curve reloaded from Word Package 4. Okay? What we'll do now? With these segments, we intersect this curve. With those intersections, we can get a kind of parametrization of these spine curves according to these segments. Now we can look for these points over there, and using these ratios, calculate interpolation. Okay? So you can run interpolation. Oh, interpolation is this. And you guess what? Is good, is bad? Well, in most cases, the idea of the project is avoiding to have a new X-ray. So you not have an X-ray. But in our case, as we are validating, we have also T1. So you can load X-ray.
That's good.
Yeah? Well, yeah. No, you've seen there are some errors, of course. You can load one. Okay. Again, you see there is a problem with size and alignment because we don't have a relationship of any kind. That's a problem we'll always have. If we don't have a mapping, we cannot align data. It's impossible. because in some cases photometric is like this, and in other cases X-ray is like this, or a bit there. So you always need the mapping.
Do you have some measure of how similar the surface?
Sorry?
Do you know how similar the photo to 3D surface is? Do you have some measure of that?
Measure of similarity between this and this?
Between the two surfaces.
Between?
The two surfaces. 3D. Photometric.
Well, the similarity is calculated point to point in the match.
Do you know, are they similar or are they very different? Do you know, can you say?
How different? Well, we have a measure of the quality of fitness between both surfaces.
I have.
We can do it later.
Did you try to put them on each other, make the difference between those two surfaces?
Difference?
Yeah.
A great difference?
No.
For instance, if you use this and this in the same, you will get a very dense mesh because
this
it's the
this
same.
measure should also, I mean, for very similar surfaces, this would be very.
I'm just asking.
That could be used as an indicator.
I don't know how much the surface change for the patient. How long is the distance from time?
6 months.
6 months minimum. 6 months minimum.
And
6 months, yes.
it's probably changed a lot.
Well, we have not tried with.
It depends if they have a brace, it depends if it changes really.
So, well, in this case, as we also have the cure for T1, because we have all the data from the project, we can load that. And now, as you have seen, the data is aligned. As you can see, this is a case I have mentioned before. The arms are like this in photometric, but in X-ray, in this case, are open. And as now it's aligned, you can see the deviation between the X-ray and our interpolation. As you can see, there are some misalignments here, there are some errors. In some of the cases it's better, perhaps here. So, well, depends a little bit. There are many factors that are involved in the quality. This is how an evaluation will be done. You have to follow, in this case, the same procedure. You have to load X-ray and photometric, another photometric here, make the matching, then an asymmetry, and finally an interpolation. You get this score, and you see.
And you can compare.
You can visually compare if the interpolation fits well. Not in this case, it's not very good, but there are worse cases and better cases. It's a kind of a visual comparison with the real X-ray. So, as regards the measure, we have implemented this godness of fit, which is also mentioned in a document that Berg, his author, you can remember. He uses root mean square error to make comparisons between surfaces. In this case, we have implemented it, but we cannot compare with the paper of the author because he has not given us detail about the results. We have just included it because it's mentioned in the project. So, well, you can run it anyway. It will give you a measure in millimeters. There is also a visual representation here. You see now the dots have become in gray color. You should have, if the matching is okay, the variations of gray colors will be solved. If there are sharp variations of color, be careful. You are having probably some more error. You have to take care. And you probably have to increase the coverage and retry. Okay? So, well, this is, let's say, the basic tutorial of how this software works. There are some more options I have not explained that to you just to